Hello, you're welcome to our physics class. And in physics today, we shall be looking at the topic elasticity. When we hear elasticity, what comes to mind is a spring that is able to stretch or to compress. So we say that a body is elastic if it regains its original strength and size after undergoing a stretching or a compression. Now, if an elastic body such as a spring is placed under a weight, so let's say that we have a spring such as this and it was placed on a weight. It stretches, so the length which was at first this will tend to increase because of the weight that was placed on it. So we have a change in the length of the spring, and when the weight is removed, it will return to its original length. So now let us have a weight that is very heavy like this. What will happen is that when you place the weight on the string or the spring and it is removed, the spring will end up not returning to its original length. The person that studied the elasticity of springs or materials of such came up with a law which is called the Hooke's law. This law states that provided the elastic limit is not exceeded, the extension, that is E, in an elastic material such as wire is proportional to the load or applied force. From this law, we can derive that the force is proportional to the extension, where when we remove the proportionality sign, it is replaced with Ke, where K is a constant, and that is what we call the elastic constant. The unit of force here is Newton. The unit of extension here is in meter. The unit of this elastic constant is Newton per meter. Another name for this force constant is stiffness. We have another derivative of the Hooke's law. And the other derivative of the Hooke's law tells us that if a force is applied to a particular length of a wire, which has a cross-sectional area and produces an extension, hence we have that the force over the cross-sectional area is proportional to the extension all over the original length. Now this particular equation is applicable if the elastic limit is not exceeded. Now from this we have force over area, and another word for this force over area is called tensile stress, while this extension over the original length is called tensile strain. Here we have Newton over meter squared, so the unit of tensile stress is Newton per meter squared. The tensile strain has no unit because we have meter and meter. Now the ratio of tensile stress to tensile strain gives us what we know as the Young modulus. The ratio of tensile stress to tensile strain gives us what we know as Young modulus, which is represented as E. So the E is what we call Young modulus. The unit of Young modulus is Newton per meter squared. Now we have an experimental verification of the Hooke's law. With it, we have a graph showing load against extension. Now we are saying that we have a spring which a load is attached to and produces an extension. Now from this graph, we have a straight line from the origin here up to this point. Along this straight line, when a load is placed on the string, now let's say the load is of this value, this spring will still return to its original length. That is, if a load of this particular weight or of this particular mass is placed on a spring, the spring will return to its original length. But if we place a little more load on the spring will end up not being able to return to its original length when it is removed. And when we increase the load further, we have another point here, which is known as the maximum load which the spring can take. At this maximum load, any further load on the spring will lead to a breakage of the spring, which we know as the breaking point. Alright, so all these points on this graph have their meaning. Let's call this A, B, C, and D. Point A is known as the elastic limit, and B is known as the yield point. C is known as the maximum load point, and D is known as the breaking point. So over here, this is the point, this is the whole area of elasticity of the spring. But between A and B, when the load is increased beyond the L1, you find out that the spring stretches permanently and it does not return to its original length. So when the load is continually increased, we keep on having this, and then between C and D, what happens is that the wire will cut because the load has become too heavy. So all the way from here from A to D, the wire will lose its elasticity. Alright, and lastly, we look at work done in stretching springs and elastic strings. We have the work done to be average force multiplied by extension, and this is taken as half Fe or half Ke squared. We derived this Ke squared from Fe because you know that F equal to Ke. So when you substitute Ke for F, you would arrive at this. We shall be using these formulas to solve questions under elasticity. This question says a spring of natural length 3 meter is extended by 0.01 meter by a force of 4 Newton. What will be its length when the applied force is 12 Newton? Alright, so in this question, we're given a spring that has an original length of 3 meter and it was extended by 0.01 meter by a force of 4 Newton. Now we're not told to find the new length when the force is increased. So when we have a new force of 12 Newton, what will be the new length? So first is, for us to do this, we need to find our constant, which is the elastic constant, and we would apply it in order to solve this. So what we have here is that our elastic constant equal to force over extension. Here the force is 4 and the extension is 0.01 meter. Knowing that we all have this unit as in SI units, and so this gives us 400 Newton per meter. So here is our force constant. Next is we'll apply this elastic constant to derive our extension when a force of 12 Newton is placed on it. And so we have that F equals to Ke. So extension equal to force over the elastic constant. The force is 12 and the elastic constant is 400, and that gives us 0.03 meter. That is the extension when a force of 12 Newton is placed on it. You can see that it increased beyond the 0.01. Now the question now says that we should find the length, the final length when we have that force on it. Hence our original length is 3 meter plus the extension, which is 0.03 meter, and that would yield 3.03 meter as the answer. If a spring has a stiffness of 950 Newton per meter, what work will be done in extending the spring by 60 millimeter? Here, a spring has a stiffness, and we said earlier that stiffness is the same thing as the elastic constant. So the stiffness is 950 Newton per meter. We are looking for the work done if we have an extension of 60 millimeter. So what we'll do in this question first is to convert the 60 millimeter into meter. So that's divided by 1000, and that gives us 0.06 meter. Next, we have the fact that work equal to half ke squared, since what we were provided with are the elastic constant and extension. Hence 1/2 times the constant, which is 950, multiplied by the extension, that's 0.06 squared. This gives 1/2 times 950 multiplied by 0.0036. Here we have 475, and when we multiply this out, we'll have 1.71 joules as the work done. The next question says that a spring of 20 centimeter long is stretched to 25 centimeter by a load of 50 Newton. What will be its length when stretched by 100 Newton, assuming that the elastic limit is not reached? Alright, so in this question, we're given an original length of 20 centimeter, and it was stretched to a new length, which is 25 centimeter by a load. The load is represented as the force, which is 50 Newton. We are asked to find the new length if the force is increased to 100 Newton. Alright, and it's assumed that the elastic limit is not exceeded. So for us to solve this, what we'll do first is to find the elastic constant over here. We have that the elastic constant equal to force over extension. Here the force is 50 Newton, and then our extension, to get our extension, we have it as 25 minus 20, and that is 5 centimeter, right? So that is the extension, but we'll not use centimeter because we have to work in the SI units. Alright, so we'll make it divided by 100, that gives us 0.05 meter. So we shall use this as the extension, that's 0.05. 50 divided by 0.05 gives us 1000 Newton per meter. So we have our elastic constant. Next is to find the extension when we have a force of 100 Newton. So we have that extension equal to force over the elastic constant. Here our force is 100 Newton and elastic constant is 1000, and that gives 0.1 meter. So that is the extension produced. We're asked to find the new length with this particular force. So the original length is 20 centimeter plus the new extension. Now we'll convert this extension into centimeter by multiplying by 100, and that gives 10 centimeter. So the new length is 30 centimeter. Here's a question which says, if a force of 100 Newton stretches a spring by 0.1 centimeter, find A, the elastic constant, B, the work done in stretching the spring 0.3 centimeter if the elastic limit is not exceeded. So in this question, we have a force of 100 Newton and it stretched the spring by 0.1 centimeter. So first is to find the elastic constant. The elastic constant is equal to force over extension. Here we have 0.1 centimeter as the extension, so we'll convert it into meter, that is divided by 100, and that gives us 0.001. Hence the elastic constant equal to 100 over 0.001, and that gives 100,000 Newton meter, which is same thing as 10 raised per 5 Newton, per meter. Next, B, we're asked to calculate the work done in stretching the spring by an extension of 0.3 centimeter if the elastic limit is not exceeded. So we have that work done equal to 1/2 ke squared. The elastic constant is the same since the elastic limit has not been exceeded. So we have it as 1/2 times our force constant, which is 10 raised per 5 multiplied by our extension, which is 0.3. Now we'll not use 0.3 centimeter, rather we'll change it to meter. We'll divide by 100, that means we have 0.003 meter. So we'll use that 0.003 squared. And so when we multiply all this out, we will have 0.45 joules as the work done in stretching the spring. This next question says a string of length 4 meter is extended by 0.02 meter when a load of 0.4 kilogram is suspended at its end. What will be the length of the string when the applied force is 15 Newton, taking acceleration due to gravity to be 10 meters per second? So here we have a string of length 4 meter and it was extended by 0.02 meter when we have a load of 0.4 kilogram. Now we have to find the length of the spring when we have a new force of 15 Newton. Alright, so what we need to do is we will convert this into weight, which is by multiplying by 10, that is 4 Newton. So we are looking for the length of this string. Alright, so we are looking for the new length. So first we get the elastic constant, which is K equal to F over E. Here the force is 4 Newton and the extension is 0.02 meter. And this gives us 200 Newton per meter. Next, we'll apply the elastic constant here to get the extension. So we have that extension equal to force over the elastic constant. The force here is 15 Newton and the elastic constant is 200. And that gives us 0.075 meter. Hence, the new length will be the original length, which is 4, plus 0.075 meter. And that gives us 4.075 meter. Here's a new question which says that an elastic material has length of 36 centimeter when a load of 40 Newton is hung on it, and a length of 45 centimeter when a load of 60 Newton is hung on it. The original length of the string is what? So we have an elastic material which has a new length of 36 centimeter when we have a load of 40 Newton, all right, on it, and then the length increases to 45 centimeter when we have a force of 60 Newton attached to it. Now we are told to find the original length. Now in each case we do not know the original length, neither do we know the extension. But one thing we should note is that their elastic constants are constants. Hence, so we can have it here that the extension equal to the new length minus the original length. Likewise here, new length minus original length. So we have the extension to be equal to 36 minus, let's take the original length to be x. So that's minus x. And here we have also 45 minus x. That is the extension. We bring in our formula that says that the force constant equal to force over extension. So here it's also applicable to this place. Now what we'll do is that since the constants are the same thing, we'll equate the two equations. So the force here is 40 Newton and the extension here is 36 minus x equal to the force over here is 60 Newton and the extension is 45 minus x. So we cross multiply. 40 will multiply 45 minus x, 60 will multiply 36 minus x. So we have 60 into brackets 36 minus x. So 40 minus 45 would give 1800. Then 40 minus x is 40x. Alright, equal to 30 multiplied by 36 gives 2160. Then 60 times x is 60x. We collect the like terms. So we have 60x minus 40x equal to 2160 minus 1800. 60 minus 40 gives us 20x. Then 2160 minus 1800, that gives 360. So x equal to 360 divided by 20. And so we have 18. Hence, the original length equal to 18 centimeter. This next question says that a copper wire was subjected to a tensile stress of 7.7 times 10 raised per 7 Newton per meter squared. Calculate the tensile strain of the wire, taking Young modulus to be equal to 1.1 times 10 raised per 11 Newton per meter squared. Here, we're given the tensile stress to be 7.7 times 10 to the power of 7 then Newton meter per meter squared, and then we're given the Young modulus as 1.1 times 10 raised per 11 Newton per meter squared. We are told to find the tensile strain. Yes, we have that Young modulus equal to the tensile stress over the tensile strain. So the tensile strain is equal to the tensile stress over the Young modulus. So we have the tensile stress to be 7.7 times 10 to the power of 7 over the Young modulus to be 1.1 times 10 to the power of 11. So we have 7 times 10 raised by 7 minus 11. So 7 times 10 to the power of minus 4. That is the value of our tensile strain. You know that tensile strain does not have any units. Next question says that if a wire 30 centimeter long is extended to 30.5 centimeter by a force of 300 Newton, find the strain energy of the wire. Simply put, what is the work done to extend the wire? Alright, so we have the original length of the wire as 30 centimeter long and the new length is 30.5 centimeter long. Then the force is 300 Newton. We are told to find the work done on the wire, and here we have our work done equal to half Fe. Now our extension is 30.5 minus 30, and that gives 0.5 centimeter, which is converted into meter by dividing by 100. So we have 0.005 meter. And so we have 1 over 2 times force, which is 300, multiplied by extension, which is 0.005. So 150 multiplied by 0.005, that yields 0.75 joules as the work done, or better still, the strain energy of the wire. This question says the diagram shown is a force extension curve of a piece of wire. The energy stored when the wire is stretched from E to F is dash. So here we have our E and we have our F here. We have P here and we have Q over here. So the wire was stretched all the way from E to F, that is from here to this place. So what we could do is to trace our points onto the X and Y axis. So to find the extension and the energy stored, what we could do is first, what's the extension? The extension is 0.1 minus 0.05 in meter, and that gives us 0.05 meter. And what is the force that was applied between those 2 points? The force that was applied is 0.2 minus 0.1, and that gives us 0.1 Newton. Now to calculate the energy stored, we have that the energy stored equal to half Fe. So we have 1 over 2 multiplied by the force, which is 0.1, times the extension, which is 0.05. And when we multiply this, that is 0.5 times 0.1 times 0.05. That gives 0.0025 joules, which is also equal to 2.5 times 10 to the power of minus 3 joules. Next question, which says that given that Young's modulus for aluminium is 7.0 times 10 to the power of 10 Newton per meter squared, and density is 2.7 times 10 raised power 3 kilogram per meter cubed, find the speed of the sound produced if a solid bar is struck at one end with a hammer. Here is an introduction of velocity and density into Young modulus. We are given the Young modulus as 7 times 10 to the power of 10 Newton meter minus 2, and we are given a density which is 2.7 times 10 raised power 3 kilogram per meter cubed. We have to find the velocity. There is a formula that relates Young modulus and density, and that is that it is the square root of the Young modulus over the density. Hence, we have the square root of the Young modulus, which is 7 times 10 to the power of 10, over the density, which is 2.7 times 10 raised power 3. So 7 divided by 2.7, that gives 2.59. Then times 10. Now this raised power 3 moves up to become 10 minus 3. And so we have 2.59 times 10 raised power 7. Don't forget, we still have our square roots outside. So next, to find the square root of this, we could make this 7 an even number by taking 1 from here and bringing it here. So it will become 20.59 times 10 to the power of 6, and then the square root of all this. The square root of 20.59 gives 5.1 approximated times 10 to the power of 6. Then this square root will become raised power half. To understand this, you can check our topic on indices mathematics. It will give you a better understanding of it. So here we have 5.1 times 10 raised power 3. So this is the speed of the sound produced. Yeah, this next question says that a force of 500 Newton is applied to a steel wire of cross-sectional area of 0.2 meters squared. The tensile stress is what? So we are given that our force equal to 500 Newton and is applied across a cross-sectional area of 0.2 meter squared. We have to find the tensile stress, and we have that tensile stress equal to force over area. Here our force is 500 and 0.2 is the area, so that is 5,000 of it, and that produces 2,500 Newton per meter squared as the tensile stress.